So far, we understood multi-objective optimization in general and how to deal with it using conversion to single objective optimization. And also, we understood how to solve it ideally using Pareto front concepts. Now, we dive into some specific techniques to solve multi-objective optimization problems. We are interested in evolutionary multi-objective techniques. So actually, these techniques employ evolutionary algorithms to find and optimize a set of solutions that represent trade-offs among multiple conflicting objectives, reflecting the diversity of possible solutions in a complex decision-making scenario. So they are inspired from nature and particularly the evolutionary mechanisms. So this set of techniques actually are inspired from nature. That's why we call them bio-inspired, and particularly the evolutionary mechanisms, the evolutionary theory. Population approaches in optimization offer several advantages. They enable the simultaneous exploration of multiple solutions, leading to a faster search process. So they are quite fast and they converge quicker than other approaches. These approaches excel in navigating intractable combinatorial space where finding solutions can be challenging. Additionally, population-based methods often incorporate niching, promoting solution diversity. This versatility makes population approaches highly effective, particularly in complex optimization scenarios. Evolutionary multi-objective optimization is driven by three key objectives: achieving convergence on the true Pareto frontier, maintaining diversity in the solution space, and doing so with computational efficiency, which means that they are trying to converge to the true Pareto front, not only to approximation, and also they are trying to maintain diversity in solution space, which means that they will try to obtain all the best combinations among all the Pareto fronts, and they try to do so in a computational efficiency way, which means that they are trying to make it in a short, quick time. The algorithm aims to find the optimal trade-off solutions, explore a diverse set of solutions, and deliver high-quality outcomes within a reasonable computational cost. It's essential to differentiate between methods and mechanisms in the context of evolutionary multi-objective optimization. So, methods such as NSGA-II that we will study in this lecture and SPIA are complete, standalone algorithms designed for multi-objective optimization. On the other hand, mechanisms like, for example, epsilon dominance and L dominance are additional calculation embedded within these methods to enhance specific aspects of their performance, which means that the method is standalone algorithm that can solve the problem, but the mechanisms are only additional techniques embedded inside these methods in order to achieve some certain level of accuracy, or sometimes just to play around the hyperparameters and so on. So the distinction highlights the comprehensive nature of evolutionary multi-objective optimization methods and the refinements introduced through mechanisms for more targeted optimization. One specific algorithm that we will study in this lecture is non-dominated sorting genetic algorithm 2, which is proposed by Deb and al. In 2000s, and it's characterized by four key features. It incorporates an explicit diversity preserving mechanism, and it also prioritizes non-dominated solutions. The third feature is that it conducts crowding comparisons, and the last feature is that it follows an elitist principle. These four key features collectively contribute to the algorithm's effectiveness in multi-objective optimization, ensuring a balance between exploration of diverse solutions and exploitation of non-dominated ones. We will come back later to this terminology. We will come back in the next slide to explain all of these notions and mechanisms. The non-dominated sorting genetic algorithm too shares similarities with traditional genetic algorithms. Drawing inspiration from biological operations, NSGA-II treats candidate solutions as individuals within a population, which means that every single individual is considered as candidate solution. These populations consist of multiple individuals, and the algorithm aims to combine them strategically to generate new individuals with the potential for improved performance. So each individual is characterized by a chromosome which represents parameters that define the solution space. This approach aligns with the principles of genetic algorithms, contributing to the algorithm's effectiveness in optimizing multi-objective problems. As we have said, the non-dominated sorting genetic algorithm too is a multi-objective optimization algorithm that efficiently searches for Pareto-optimal solutions. But how this is done? So let's explain the process and how the algorithm works step by step. So the workflow starts with initialization, where NSGA-II begins by generating an initial population of candidate solutions. So as we have said before, this is a population-based algorithm, which means that we need to have, in the first iteration, we need to have a population, a set of individuals, and each individual will be considered as candidate solution. The next step is the evaluation. In this step, the algorithm will evaluate the fitness of each solution in the population based on multiple objective functions. The goal here in this step is to determine how well each solution performs across all defined objectives. Then, after the evaluation and the computation of fitness values, then it comes to selection, where the algorithm selects individuals for the next generation by favoring those in higher non-dominated fronts and with larger crowding distances. We will come back later to define every single notion here and how it can be computed and accomplished. Anyway, so this balances the exploration of solution space, diversity, and the exploitation of good solutions, non-dominated fronts. After the selection, the selected individuals will undergo genetic operations such as crossover and mutation in order to create new candidate solutions for the next generation. So in this step, we will try to modify our individuals in order to improve them for the next generation. So in the next generation, we will have new solutions along with some of the best from the current generation from the next population. So the process iterates until a stopping criterion is met, such as reaching a maximum number of generations or a convergence threshold. Keeping the best solution from the current generation is called elitism. So this is a good notion, actually, an important one to remember. What is elitism? Elitism is the process where we keep the best solution from the current generation to the next one. So this process in a whole, this workflow is repeated either for a specific number of generations until a specific number of generations is achieved, or until a certain condition is fulfilled. By iteratively applying these steps, NSGA-II evolves a population of solutions toward the Pareto front, the optimal front, providing a diverse set of trade-offs solutions for multi-objective optimization problems. In this slide, we give a brief description of the low-level workflow of the algorithms, and we will come back in the next slide to explain everything in details. In the first step of each iteration, we start by the best solutions from the previous iteration, called PT, and we generate from them a new offspring noted QT using genetic operations. So here in the first step, we have PT, which is like the best solutions that we had from the previous iteration, and the offspring that we create from PT using genetic operators, and that we note QT. That's fine. Then we will use a non-dominated sorting technique in order to categorize solutions into different non-dominated fronts. So the second step is to rank the solutions based on their non-domination into different non-dominated fronts, where a solution in a front is not worse than any other solution in the same front and strictly better than those in the previous fronts. So here we will have a set of Pareto fronts. We will come back to this into the next slides with a figure that illustrates how this is done. Then we will use a crowding distance assignment in order to choose among the best solutions and remove some of them. So this crowding distance assignment is done within each front, where solutions are assigned a crowding distance that measures how close they are to their neighbors. This step helps to maintain diversity in the population. We will come back to this in detail. After these two operations, we exclude the half of the population and we keep only the best half. So at the end, we will have like the best solutions in our current iteration. So in this slide, we explained how one iteration is done in the workflow of NSGA-II. In the production of offspring within the non-dominated sorting genetic algorithm 2, two fundamental genetic operations are employed: crossover and mutation. These operations involve combining genetic information from parent solutions to generate new offspring, introducing diversity and potential improvements. Actually, these techniques have as goal to improve the solutions from one generation to another, and also to create some randomness in order to move and search in the feasible space. A crucial strategy in this process is called elitism, as we have explained before. So elitism ensures that high-performing individuals from the current population, PT, are preserved and merged with the newly created offspring. This strategic combination prevents the loss of important genetic information and helps to maintain the best solutions. This will contribute to the algorithm's efficiency in exploring and exploiting the solution space for multi-objective optimization. Then, in the next step, we need to rank the solutions. In the ranking phase of algorithms like NSGA-II, both parent and child solutions are combined. The ranking process involves assigning solutions to different ranks based on their dominance relationships. The procedure is as follows. Non-dominated points, which are solutions non-dominated by any other solutions in the combined set of parents and children, should belong to the first rank. So the first rank includes the solutions that are not dominated by any other solutions in the list of parents plus children. Then In the subsequent ranks, the non-dominated solutions from the remaining set are assigned to the second rank, and then which are like dominated by all, which are dominated only by the first rank and dominates all the other solutions. And this process continues for subsequent ranks. Okay, so this is done for the first rank, second rank, third rank, and so on and so forth. And each rank dominates all the solutions except for the previous ranks. An important consideration in case of ties is the selection based on crowding distance, a technique known as niching. If a parent and child have the same rank, their selection is determined by their crowding distance, which measures how close solutions are to their neighbors. This additional step helps maintain diversity in the population, preventing premature convergence to specific regions of the solution space. This is what we will see in the next slides. But overall, this ranking approach is in organizing and selecting solutions based on their Pareto dominance and crowding distance, facilitating the evolution towards a diverse set of high quality solutions of multi-objective optimization. Crowding distance is a measure used Crowding distance is a metric used in multi-objective optimization to estimate the density of solutions surrounding a particular solution. So this is needed when the parent and children have the same rank and and belong to the same front, and we need to split the population in the half in order to keep only the best half of the population. So the crowding distance assignment procedure involves the following step. So first we should initialize, which means that we should have set I, which is a set of solutions in a front, and then we should initialize the distances dy. Y is an integer from 0 to L. So and then the next step is the objective sorting. So for every objective function, we should sort the set in the worst order of Fm and find the sorted indices vector Im. So after the sorting, we have to assign crowding distances. So within each front, crowding distance is calculated for each solution. This involves computing the distances between neighboring solutions along each objective dimensions. Solutions are sorted based on their crowding distances. Then we update the crowding distance. So the solutions at the ends of the front are assigned infinite crowding distance to ensure that they are preserved for diversity, and the solutions in between, as shown in the figure, are assigned crowding distances based on the average distance to their neighboring solutions along each objective dimension. So after calculating crowding distances for all solutions, individuals are selected for the next generation. NSGA-II typically employs a combination of non-dominated sorting and crowding distance to select individuals for the next generation. Solutions with smaller crowding distances are preferred as they represent different regions of higher density in the objective space, thereby preserving diversity. This visualization provides an insight on the optimization of two objectives. The first objective function is x squared that we have used previously in the genetic algorithm, and the second objective function is x minus 2 square. The figure shows generation by generation how the Pareto front evolves. So at the end we will have very accurate parabolic Pareto front where one of the objective functions, either f1 or f2, is in its optimal solution. And the Pareto front shows the non-dominated solutions, where if we change or if we change one of them, so there is no improvement in one of the objective functions. In NSGA-II, and also it's the same on all other in many other algorithms, balancing diversity and convergence is crucial for effective multi-objective optimization. In fact, the diversity ensures that the algorithm explores a wide range of solutions across Pareto fronts, preventing premature convergence to suboptimal regions. So NSGA-II promotes diversity through mechanisms such as non-dominated sorting and crowd distance assignment, as we have explained before, which encourages the maintenance of individuals in both densely populated and less crowded regions of the Pareto fronts. By prioritizing diversity, NSGA-II ensures that the optimization process continues to explore and discover novel solutions throughout the space, providing decision makers with a comprehensive representation of the trade-offs between conflicting objectives. On the other hand, convergence is essentially very important for identifying high-quality solutions that closely approximate the Pareto fronts. NSGA-II achieves convergence by guiding the population towards regions of higher quality solutions through selection mechanisms and genetic operators like crossover and mutation. These operators facilitates exploration of the search space and also generation of offspring with the best objective trade-offs. Anyway, so this is what you need to keep in mind. By balancing diversity and convergence, NSGA-II strikes a harmonious approach to multi-objective optimization, ensuring that the algorithm effectively explores the solution space while converging towards a set of high-quality solutions that accurately represent the trade-offs inherent in the problem that we are trying to solve. I would like to conclude by stressing on the understanding of exploration and exploitation, because there are two fundamental strategies in optimization algorithms like NSGA-II. Exploration involves searching the solution space broadly to discover new regions that may contain better solutions, and this allows the algorithm to uncover diverse options and avoid premature convergence to local optima. In NSGA-II, exploration is facilitated through mechanisms like genetic operators, such as crossover and mutation, which introduce diversity by exploring new solution combinations. On the other hand, exploitation involves intensifying and exhaustively searching around promising regions of the solution space where high quality solutions are likely to be found. So we are trying to exploit what we achieved so far. So NSGA-II achieves exploitation by selecting individuals from regions of higher quality, favoring those with better non-dominated ranks and smaller crowding distances. By balancing exploration and exploitation, NSGA-II effectively navigates the trade-off between discovering novel solutions and refining the population towards regions of higher quality, ultimately leading to a diverse and converged set of Pareto-optimal solutions. Anyway, so this is actually something very interesting to understand, and it helps you actually to fine-tune the hyperparameters of different operators and tackle the multi-objective optimization accurately. So let's conclude our lecture for today. NSGA-II, it's a non-dominated sorting genetic algorithm. Two, it boosts several advantages that contribute to its effectiveness in multi-objective optimization. One remarkable advantage is its explicit diversity preservation mechanism, which ensures that the algorithm maintains a diverse set of solutions across the Pareto front. So this mechanism, facilitated by techniques like non-dominated sorting and crowding distance calculation, prevents premature convergence to suboptimal regions and promotes thorough exploration of the solution space. Additionally, NSGA-II exhibits a good computation complexity with an overall complexity of at most OMN square, where M represents the number of objectives and N denotes the population size. So it's anyway a good complexity, computation complexity. It's not like very high. And NSGA-II incorporates elitism, a strategy that guards already discovered Pareto-optimal solutions from being removed. And this will enhance stability and reliability of the optimization process. However, NSGA-II presents also some drawbacks. For example, the crowded comparison approach employed by NSGA-II can potentially restrict convergence, particularly in densely populated regions of Pareto fronts. So this limitation might impede the algorithm's ability to accurately converge towards the true Pareto fronts, because we exclude some of the solutions in the high density regions. And we may end up in most of the cases to near optimal solution, not the most optimal, like the optimal solution. Additionally, the computational overhead of non-dominated sorting may be sometime for complex problems where the population should be very high, then the computation will increase. Despite like this drawbacks, so NSGA-II remains one of the most used algorithms, and it has influence in many fields and many applications, thanks to its balance of exploration and exploitation strategies, and also its ability to generate diverse and high quality Pareto optimal solutions.